Imagine waking up to discover that every map humanity has ever drawn of our global climate was measured from the interior of a tightly sealed, artificially heated greenhouse. You might have gathered exceptionally precise temperature data over decades, and your mathematical models might be flawless, yet your baseline calculation of the planet's true climate would be systematically distorted by the invisible walls surrounding you. For generations, astronomers have looked out into the deep cosmos with a profound, unspoken confidence that our position in space is entirely ordinary. We assume that the vast patches of the universe we see around us represent a fair and typical cross-section of the macroscopic cosmos. But what if our modern instruments are falling victim to a colossal cosmic illusion? What if the greatest mystery in contemporary astronomy, a fierce, mathematically rigorous disagreement over how fast the fabric of reality is, expanding, is not a flaw in our telescopes, but a direct consequence of our cosmic address? Deep space surveys mapping the distribution of matter across billions of light years have quietly revealed a staggering structural reality. Our home galaxy, the Milky Way, along with our local cosmic neighborhood, is trapped inside an immense, nearly invisible desert of space. We're drifting through a gargantuan architectural hollow known to science as the Keenan, Barger, and Cowie underdensity. This cosmic hole stretches an astonishing 2 billion light-years from side to side, making it one of the largest structural features ever detected by human intelligence. Within this barren expanse, the density of matter drops by roughly 20% compared to the rest of the observable universe. This local emptiness does more than just isolate us in a quiet corner of creation. It actively warps our perspective of macroscopic reality. By altering the gravitational landscape on a grand scale, this silent void creates a powerful outward pull, causing whole clusters of galaxies to rush away from our position at blistering speeds. This systematic motion mimics a hyper-accelerated cosmic expansion, tricking our finest telescopes and throwing our fundamental cosmological equations into deep confusion. Are we measuring the true expansion rate of the cosmos, or are we merely observing a distorted local signal from inside a giant bubble? If our location in space is this unusual, can we truly trust our calculations regarding the absolute age of the universe, the nature of dark energy, or the ultimate destiny of time and space? In this journey, we will step backward from our daily terrestrial lives to map our true coordinates in the cosmic web. We will explore the remarkable detective work that exposed this hidden hollow, dissect the counterintuitive physics that govern empty space, and investigate how our presence inside this immense desert might finally solve the most urgent crisis in modern astronomy. To comprehend how a colossal empty space can distort our understanding of the universe, we must first look at the foundational tool of modern cosmology, the measurement of cosmic expansion. For nearly a century, astronomers have known that the universe is growing. This discovery implies that galaxies are moving away from one another, stretching the very fabric of space and time. To quantify this movement, scientists rely on a specific value known as the Hubble constant. This number acts as the ultimate cosmic speedometer, telling us exactly how fast a galaxy is receding based on its distance from Earth. If the universe is uniform and governed by identical laws in every direction, measuring this cosmic speedometer should yield the exact same result, regardless of the method or instruments used. Yet, as our technology has grown incredibly precise over the last few decades, a deep and unsettling mismatch has emerged. This mystery is known to astrophysicists as the Hubble tension. The problem behaves like a puzzle where the two primary pieces refuse to fit together. When scientists calculate the expansion rate by looking at the ancient universe, they get one specific answer. To do this, they analyze the cosmic microwave background radiation, which is the faint, fading afterglow of the Big Bang itself. This light represents a pristine snapshot of the infant cosmos when it was only 380,000 years old. Satellites like the Planck spacecraft have mapped this ancient light with exquisite detail. By plugging these microscopic temperature fluctuations into our standard cosmological models, researchers calculate that the universe should currently be expanding at a rate of approximately 67 kilometers per second per megaparsec. A megaparsec is an astronomical unit of distance equivalent to roughly 3.3 million light-years. However, When astronomers measure the expansion rate using a completely different method focused on the modern, nearby universe, the cosmic speedometer gives a significantly higher reading. This second approach uses a technique called the cosmic distance ladder. Instead of looking at ancient radiation, scientists observe specific nearby objects with known, reliable brightness. These objects include Cepheid variable stars, which pulse with a rhythm tied directly to their intrinsic luminosity, and Type 1a supernovae, which are the cataclysmic explosions of dying white dwarf stars that burst with a uniform energy output. By comparing how bright these objects truly are to how faint they appear from Earth, astronomers can calculate their exact distances. When they combine these distances with the object's redshifts, which is the stretching of light toward longer, redder wavelengths caused by motion, the local expansion rate consistently comes out to roughly 73 kilometers per second per megaparsec. The difference between 67 and 73 is about 9%. While 9% sounds small in everyday life, in the precise realm of astrophysics, it represents a profound crisis. Both measurements are incredibly meticulous. The statistical margins of error have shrunk so low that this mismatch cannot be explained away as a simple math error or a faulty instrument. The statistical significance of this tension has crossed a strict boundary known as 5 sigma. In plain terms, this means there is less than a 1 in a million chance that the disagreement is a random fluke. For years, this discrepancy has forced researchers to wonder if our core understanding of cosmic history is missing a vital component. If the universe is truly expanding much faster today than it did in the deep past, it implies that the rate of expansion has accelerated unexpectedly. This would mean the universe reached its current size much quicker than previously assumed, which would drop the calculated age of the universe from 13.8 billion years down to just 12.7 billion years. As we will see, this introduces an impossible paradox involving ancient stars. But what if the laws of gravity are not broken? What if the universe is not actually expanding faster everywhere, but our local measurements are being severely contaminated because we are observing the cosmos from the inside of a massive, underdense structural hole? The realization that our local universe might be lying to us began to take shape through a patient and methodical counting of galaxies. In 2013, 3 bold astronomers set out to map the structural layout of our local cosmic neighborhood. Ryan Keenan, Amy Barger, and Lennox Cowie undertook a massive analysis that would eventually bear their initials, becoming known to science as the Keenan, Barger, and Cowie underdensity, or simply the KBC void. Instead of looking globally at the entire sky as a singular entity, they meticulously cataloged the positions, distances, and distributions of approximately 35,000 individual galaxies. They utilized deep 3-dimensional redshift surveys, which allow scientists to determine exactly how far away a galaxy sits by measuring the degree to which its light has been stretched by the expanding universe. As the data poured in and the 3-dimensional maps began to materialize, the researchers noticed a pattern that seemed completely wrong. Everywhere they looked in the nearby universe, out to a distance of several 100 million light-years, there were far fewer galaxies than the standard laws of cosmology predicted. This was not a minor localized fluctuation. The deficit was immense and remarkably consistent. The local space surrounding the Milky Way was roughly 20% more empty than the average baseline density of the broader universe. This vast, underdense bubble stretched outward in every direction for nearly 1 billion light-years from its center, creating an enormous cosmic sphere with our galaxy positioned uncomfortably close to the middle. To ensure they had not fallen victim to a systematic error or a localized distortion in one small patch of sky, the team cross-referenced their findings with multiple independent galaxy catalogs. They examined the sky from different viewing angles and accounted for the obscuring dust of our own galactic disk. The results stood firm. The structural data confirmed that humanity resides within a massive structural hollow that pushes the absolute limits of standard cosmological theories. To understand why this discovery sent shockwaves through the astronomical community, one must look at how the cosmos organizes itself on the grandest scales. The universe is not a smooth, evenly distributed fluid of matter. Instead, It resembles an intricate foam-like architectural network known as the cosmic web. This web represents the largest structural pattern found in nature. It is woven out of dark matter and regular hydrogen gas, forming three distinct structural components. First, there are nodes, which are hyperdense gravitational intersections where massive clusters of thousands of galaxies are packed tightly together, shining with a collective brilliance. Radiating outward from these nodes are long, thin, twisting threads known as filaments. These filaments form vast sheets and cosmic walls that stretch across hundreds of millions of light years, serving as the stellar highways of the cosmos. Finally, between these crowded filaments and walls lie the third major component of the web: cosmic voids. Voids are colossal, spherical pockets of low-density space. They represent the true wilderness of the cosmos, occupying roughly 90% of the total volume of the universe while holding only a fraction of its total mass. The standard model of cosmology, known as lambda cold dark matter, states that when you zoom out far enough, the universe should look essentially identical everywhere. This fundamental principle implies that if you look at a patch of space a few 100 million light-years across, it should contain roughly the same amount of matter as any other patch of the same size. Computer simulations tracking how gravity pulled matter together after the Big Bang reveal that while small and medium-sized voids are incredibly common, the formation of an underdensity as massive and deep as the KBC void is an exceptionally rare statistical event. Some advanced statistical analyses have calculated that finding a void of this scale in a standard universe represents a 10 sigma deviation from the norm. This means that if you were to simulate thousands of random universes from scratch, you might not find a single local underdensity this large in any of them. Yet, against all mathematical odds, we find ourselves living inside one. This brings us back to the counterintuitive physics that govern these deep space deserts. Voids are not completely empty vacuums. They contain sparse amounts of dark matter, occasional wisps of pristine hydrogen gas, and solitary dwarf galaxies that drift quietly through the dark. Because there is so little matter inside a void, the collective pulling power of regular gravity is incredibly weak. In these vast, lonely spaces, the dominant physical force becomes dark energy, the mysterious, uniform pressure that acts like a repulsive force, accelerating the expansion of space itself. In dense, crowded filaments, regular gravity fights a continuous tug-of-war against dark energy, slowing down the local rate of cosmic expansion. But inside a massive void, gravity loses this battle decisively. Dark energy wins without resistance, causing the interior of the void to expand much faster than the dense walls surrounding it. Furthermore, the structural imbalance triggers a spectacular phenomenon known as a cosmic outflow. Think of a massive void as a shallow valley surrounded by steep, heavy mountains of matter. Just as a ball naturally rolls downhill, galaxies positioned inside the underdense valley are gravitationally attracted to the immense, high-density walls of matter located outside the void. This means that everything inside our local bubble is actively falling outward, accelerating away from the center of the void toward the dense cosmic structures that mark its perimeter. This systematic outward rush creates a powerful velocity field that distorts our astronomical measurements. When we point our telescopes at nearby Type 1a supernovae to calculate the Hubble constant, our instruments detect two distinct types of motion. They record the universal expansion of space itself, but they also record the extra speed of this local, gravity-driven outward flight. Because our local galaxies are rushing away from the center of the whole, they appear to be receding at a hyper-accelerated rate. This local inflation explains exactly why our nearby telescopes yield an expansion speed of 73, while the ancient light of the cosmic microwave background insists the true background speed is only 67. We are not measuring a broken universe. We are simply measuring reality from the inside of a colossal, accelerating whole. The verification of the Keenan, Barger, and Cowie underdensity does far more than just settle a dispute over a cosmic number. It forces researchers to test old assumptions and completely re-examine our relationship with the cosmos. For centuries, the steady march of astronomical progress has relied on a foundational rule known as the Cosmological Principle. This sacred baseline states that on sufficiently large scales, the universe is both homogeneous and isotropic. Homogeneous means that the distribution of matter looks identical no matter where you stand in space, while isotropic means that the universe looks the same no matter which direction you point your telescope. This simple idea has allowed scientists to use relatively straightforward mathematics to model the entire history of cosmic evolution. It is a philosophy that has systematically decentered humanity from any special status. Nicolaus Copernicus showed that Earth is not the center of the solar system. Subsequent generations of astronomers proved that our sun is just an ordinary star on the outskirts of a common spiral galaxy, and our galaxy is merely one of billions floating through an indifferent infinity. Yet, the sheer scale of the KBC void challenges this worldview directly. If we reside inside an underdense pocket of space that spans 2 billion light years, then our local address is undeniably unusual. Finding ourselves positioned so close to the center of one of the largest structural hollows in the observable universe feels like a violation of the Copernican spirit, a statistical coincidence so extreme that it makes many physicists profoundly uncomfortable. If our location in space is a statistical outlier, it suggests that our picture of the early universe may need refinement. The classical model assumes that the initial quantum fluctuations generated during the first fraction of a second after the Big Bang were perfectly uniform and random across all scales. But if structural anomalies like the KBC void are real, it could mean that the early universe was far more turbulent and less smooth than our standard models assume. This architectural anomaly has become powerful ammunition in ongoing debates regarding the absolute reliability of Albert Einstein's theory of general relativity on macroscopic scales. When faced with a structure that is mathematically impossible under standard rules, science offers two distinct paths forward. The first path is to accept that we live in a highly unusual location by pure chance. The second, more radical path suggests that our mathematical model of gravity itself is incomplete. Some researchers argue that the existence of such massive voids reveals a critical flaw in how we simulate cosmic growth. They have proposed alternative gravitational frameworks, such as modified Newtonian dynamics or specialized theories of modified gravity. These alternative models suggest that the pulling power of gravity behaves differently when cosmic accelerations drop below an extremely low threshold, such as in the sparse environments between galaxy filaments. In a universe governed by modified gravity, the rate of structure formation is naturally enhanced. Matter clumps together far more aggressively into dense walls, which causes the intervening empty spaces to evacuate much faster, turning ordinary low-density regions into colossal supervoids. Under these modified rules, a structure as massive as the KBC void stops being an impossible 10 sigma anomaly and instead becomes an expected, natural consequence of cosmic physics. However, embracing modified gravity requires a steep intellectual price. While it easily explains the rapid growth of large voids, it struggles to account for the highly precise temperature patterns observed in the ancient cosmic microwave background radiation, a feat that Einstein's standard general relativity achieves with flawless accuracy. Furthermore, the void hypothesis directly rescues us from a catastrophic chronological paradox involving the age of the stars. If we reject the local void explanation and blindly accept the nearby measurement of 73 kilometers per second per megaparsec as the absolute truth for the entire universe, our calculations force the age of the cosmos down to 12.7 billion years. This creates an immediate logical breakdown. By analyzing the nuclear burning rates and chemical compositions of stellar clusters, astronomers can determine the ages of the oldest known stars in the universe, such as those found in ancient, tightly bound structures called globular clusters. These metal-poor stellar relics consistently date back to roughly 13 billion years ago. It is an immutable law of logic that a star cannot be older than the universe that contains it. You cannot fit a 13-billion-year-old star into a 12.7 billion-year-old cosmos. By proving that our local expansion measurement is an environmental distortion caused by the outward pull of the KBC void, we can safely preserve the global cosmic age of 13.8 billion years, ensuring that the oldest stars have plenty of time to form, age, and endure. To appreciate our true position within this vast architecture, we must trace our cosmic lineage across multiple nested layers of reality. The human journey has always been a story of expanding horizons. We long believed our world was an isolated stage, only to realize we inhabit a dynamic planetary system nested inside a spinning disk of hundreds of billions of stars known as the Milky Way galaxy. Our galaxy does not wander alone through the deep dark. It is gravitationally to a small family of roughly 80 galactic neighbors known as the local group. This group is dominated by two massive stellar engines, our own Milky Way and our giant celestial neighbor, the Andromeda Galaxy, which are currently locked in a slow gravitational dance, hurtling toward an inevitable collision several billion years in the future. When we look even further out, we discover that the local group is just a minor stream feeding into a much grander gravitational watershed. In 2014, astronomers mapping local cosmic velocities discovered that we belong to a colossal superstructure named the Laniakea supercluster. This name, drawn from the Hawaiian language, translates to immeasurable heaven, a title that perfectly captures its staggering scale. Laniakea spans more than 500 million light-years from edge to edge and contains roughly 100,000 individual galaxies, all flowing coherently along invisible pathways toward a central gravitational valley known as the Great Attractor. Here lies the ultimate structural paradox of our modern understanding. Despite its mind-boggling size and its population of 100,000 galaxies, the entire Laniakea supercluster is merely a sparse, lonely island trapped inside the gargantuan emptiness of the Keenan, Barger, and Cowie void. This reality forces us to understand that cosmic voids are not completely uniform, featureless voids. They possess an internal anatomy of their own. The KBC void is underdense on average, meaning that when you calculate the total amount of matter across its entire 2 billion light-year expanse, it contains 80% less mass than a typical region of space. But within this massive desert, matter still manages to form intricate small-scale structures. Laniakea represents a localized concentration of matter struggling to hold itself together, a rare oasis in the middle of a vast cosmic Sahara. Our local position is rendered even more dynamic by our proximity to another distinct, adjacent underdensity known simply as the local void. This neighboring desert begins right at the edge of our galactic family, stretching across roughly 200 million light-years of profoundly empty space. The combined gravitational physics of these nested structures creates a state of perpetual motion. Because the local void lacks the mass to pull matter toward itself, and the broader KBC void features a massive structural imbalance, the Milky Way is not sitting still. Our entire galactic home is actively plummeting through the cosmos at a blistering speed of approximately 600,000 miles per hour, which is equivalent to roughly 627 kilometers per second relative to the rest frame of the cosmic microwave background. We are participating in a massive cosmic evacuation. Our galaxy, along with a flat wall of neighbors known as the local sheet, is rushing away from the empty heart of the local void and streaming outward toward the high-density perimeters of our structural bubble. This motion is completely separate from the general, uniform expansion of space. It is a direct structural response to the uneven distribution of matter across cosmic time. The story of how these massive deserts and crowded filaments came to coexist takes us back to the absolute beginning of time and space. Immediately following the Big Bang, during an epoch known as cosmic inflation, the universe underwent an exponential burst of hyperacceleration, stretching subatomic space to macroscopic proportions in a tiny fraction of a second. This rapid expansion took microscopic quantum fluctuations, momentary ripples of uncertainty in the fabric of space, and stretched them into immense variations in density across the newborn cosmos. When inflation ended, these variations were incredibly subtle, representing differences in density of only about 1 part in 100,000. This pristine, modeled pattern was captured forever in the temperature maps of the cosmic microwave background radiation, recorded by satellites like COBE, WMAP, and Planck as an intricate tapestry of slightly warmer and cooler spots. Over the course of 13.8 billion years, the relentless power of gravity acted as the ultimate structural sculptor, a phenomenon known to physics as gravitational instability. Regions that started with a microscopic advantage in density possessed slightly more gravitational pull, allowing them to steal gas and dark matter from their surroundings. As these overdense regions grew heavier, their pulling power amplified, creating a runaway feedback loop that eventually collapsed into the first stars, galaxies, and hyperdense filaments. Conversely, the regions that began with slightly less matter lost the cosmic tug-of-war, watching their contents drain away into the heavier structures. Over billions of years, these depleted zones expanded into the colossal, hollow voids that dominate 90% of our modern sky, leaving us with a universe organized not as a smooth soup, but as a vast interconnected foam of matter and emptiness. Our presence within the great 2 billion light-year expanse of the Keenan, Barger, and Cowie void reveals a profound truth about the nature of human exploration. The environment from which we observe reality directly shapes the universal truths we try to calculate. For decades, we looked out at the distant stars assuming our vantage point was completely neutral, a flawless lens looking out onto a perfectly uniform cosmos. The discovery of this massive local desert shatters that illusion, proving that our cosmic address acts as a subtle filter, distorting our baseline measurements and forcing us to confront our own physical isolation. This spatial isolation raises an extraordinary philosophical question regarding the future of intelligence in an expanding cosmos. Because dark energy dominates the empty interiors of cosmic voids, these giant deserts are expanding at an accelerated rate, gradually thinning out the filaments of galaxies that line their borders. As the eons pass and the fabric of space continues to stretch, the cosmic horizon will inevitably shrink. Billions of years from now, a future civilization arising on a lonely planet deep within our merged, galactic remnant will look up at a night sky that has gone completely dark. The distant galaxy clusters we study today, the brilliant signatures of Type 1a supernovae, and the faint, ancient glow of the cosmic microwave background will have been pushed beyond the reachable limits of light itself. To those future observers, the universe will appear static, eternal, and completely empty, an isolated island of matter floating in an infinite, trackless void. They will have no physical way to discover the Big Bang, no standard candles to measure cosmic expansion, and no structural clues to reveal the existence of the grand cosmic web that once flourished across the cosmos. They will be prisoners of their local geography, completely unaware of the broader, dynamic reality that preceded them. We are incredibly fortunate to live in an epoch when the cosmic web is still vividly visible, when the clues of our origin remain etched into the night's sky, and when the architecture of the cosmos can still be mapped and understood. The persistent mismatch of the Hubble tension is not a failure of the scientific method, it is a profound gift. It is an astronomical beacon warning us that we cannot understand the macroscopic universe without first understanding our own hollow home. By learning to subtract the structural distortion of our local address, humanity takes its next great step toward a true, uncompromised map of reality. If this journey through the deep deserts of the cosmic web has altered the way you view our place in the cosmos, please consider interacting with this content. Support our exploration of the universe by hitting the like button, subscribing to our channel, and activating the notification bell to join us for future cosmic investigations. We want to hear your thoughts in the comment section below. Does the idea that we live inside one of the largest holes in the universe make you feel profoundly isolated? Or does it inspire you to marvel at how much human intelligence can do from the inside of a cosmic desert? Thank you for watching, for wandering through the darkness with us, and for remaining endlessly curious about the hidden structures of our magnificent, hollowing cosmos.